Here we'll introduce the limits of functions as x goes to infinity. But before we get into limits, let's look at a function you've probably seen before, y equals 1 over x. As x gets really big, what value does y seem to approach for this function? And if you'd like to review power functions like 1 over x instead, then click down here. Right, it looks like this function is approaching 0. In this lesson, we'll be proving that this is true. So to prove that this function approaches 0, we'll be using this interactive graph. This curve here is the function 1 over x, and you can drag the graph left and right to see different parts of the curve. There's also a horizontal tube here. The tube is centered on the x-axis for now, and you can change how wide the tube is by dragging these two green circles up and down. Wherever the function is inside the tube, it's colored blue, and when the function is outside the tube, it's colored orange. When every part of the function on the screen is inside the tube will turn blue. Now notice that there's a point over here where the function enters the tube. What can you say about the function at values of x greater than this point? So with the tube centered on the x-axis, it looks like the function enters the tube and then never leaves the tube. Even if we make the tube really narrow, like this tube here, we can move out along the x-axis, find where the function enters the tube, and it looks like it never leaves the tube again. Next, let's try moving the tube around to see what happens. You can move the tube by dragging this black circle up and down. Let's move the tube up here to where y is about 0.8. And let's make the tube really wide, giving it a width of 1 in either direction. Once again, it looks like the function enters the tube, but then never leaves. But what happens if we make the tube narrower, giving it a smaller width, like, say, 0.6? Right, so if we have a narrow tube centered around 0.8, the function eventually leaves the tube, because the function keeps decreasing as x gets bigger. Let's try to find places where we can center the tube so that the function never leaves the tube. 0.8 was no good, because when we made the tube narrow, the function left the tube. Let's try centering the tube at a smaller value, like around 0.5. If you set the width of the tube to about 0.6 again, it looks like the function enters and never leaves. If we set the width to a smaller value, like around 0.4, here's where the function enters the tube. What can you say about the function at values of x greater than this point? We're trying to find places where we can center the tube so that the function never leaves the tube. 0.8 was no good, and now it appears that 0.5 is also no good, because when we made the tube narrower, the function left the tube. Let's return to the tube centered at 0. Now, if each half of the tube again has a width of 0.4, the function enters the tube and never leaves. What happens if we make the tube even narrower, with a width of, say, 0.3? So even when the tube is as narrow as having a width of 0.3, it looks like the function stays inside the tube. Try out even narrower tubes. When the tube is centered at y equals 0, meaning it's centered on the x-axis, for which of these different tube widths does this function stay inside the tube? So here's what it means to say that this function approaches 0 as x gets really big. For any tube centered at 0, no matter how narrow the tube, there's a value of x beyond which f of x is always inside the tube. If you center the tube anywhere else, the function eventually leaves the tube. So if 0 really is the limit of this function, then the function had better stay inside the tube no matter how wide or narrow the tube is. Let's call the width of the tube epsilon, which is a Greek letter. We can make epsilon any number we want. It can be big, or we can make it really small. At this point, you can also use this vertical slider here to see when the function is in the tube. If the function is inside the tube everywhere on the screen to the right of the slider, the tube will turn blue. It looks like no matter how big or small we make epsilon, the function always enters and stays inside the tube centered at 0. For a tube of width epsilon, at which x-coordinate does the function enter the tube? Okay, no problem. Let's test out a few different values of epsilon and see where the function enters the tube. When epsilon equals 1, at what value of x does the function enter the tube? Right, so when epsilon equals 1, the function enters the tube when x equals 1. Now let's try out another value of epsilon. When epsilon equals 0.5, at what value of x does the function now enter the tube? Exactly. When epsilon equals 0.5, the function enters the tube when x equals 2. And when epsilon equals 0.25, or 1/4, at what value of x does the function enter the tube? Okay, so let's review what you found. When epsilon was 1, the function entered the tube when x equals 1. When epsilon was 0.5, or 1/2, the function entered the tube when x equals 2. And when epsilon was 0.25, or 1/4, the function entered the tube when x equals 4. So for a tube of width epsilon, where does the function enter the tube in terms of epsilon? So for every tube centered at 0, no matter what its width is, you know f of x always enters the tube, because for any width epsilon you pick, the function enters the tube when x equals 1 over epsilon. After the function enters the tube centered at 0, it looks like it stays inside the tube, no matter how far down the x-axis you go. How do you know this function won't just pass through and leave the tube for really big values of x? Exactly. This function is always positive. That means it can never cross the x-axis, no matter how large x becomes. So if the tube is centered on the x-axis, the function will never leave the tube. So you found that for a tube of width epsilon, f of x is inside the tube whenever x is greater than 1 over epsilon. What's the mathematical way to say that f of x is inside the tube that's centered at 0 and has width epsilon? At this point, we have all the pieces we need to say that 0 is the limit of this function. Again, here's how we've been saying that this function is approaching 0. No matter how narrow the tube is, there's a value of x beyond which the function is always inside the tube centered at 0. Suppose the tube has a width of epsilon. Then no matter how narrow the tube is the same thing as saying that the tube can have any width epsilon greater than 0. So for any width epsilon of this tube, there's a value of x beyond which the function is always inside the tube centered at 0. And you just found that saying f of x is inside the tube centered at 0 is the same thing as saying that 0 minus epsilon is less than f of x, which is less than 0 plus epsilon. And you also found where the function 1 over x enters the tube. For a tube centered at 0 and of width epsilon, 1 over x enters the tube at 1 over epsilon. So here's the mathematical way to write that this function is approaching 0. For any epsilon, or tube width, greater than 0, for all x greater than 1 over epsilon, so that would be to the right of this line here, f of x is inside the tube. That is, 0 minus epsilon is less than f of x is less than 0 plus epsilon. This statement has a lot of parts, and each requires a bit of thought. In calculus, this statement can be summarized by this equation. These two statements mean the same thing, but this one is a lot shorter to write down. You can read this as the limit as x goes to infinity of 1 over x equals 0. This means that as x gets really big, 1 over x approaches 0. It means this statement down here. Now this does not mean that when x equals infinity, 1 over x equals 0. X can't equal infinity. But as x gets very large, 1 over x approaches 0. Next, let's see if we can find the limit of another function, g, shown here. Which of these values would you say this function is approaching as x gets really big? Again, here's our function g of x. You found that as x gets really big, g of x approaches a value of 1.5, or 3/2. Here are our previous statements that said the function 1 over x approaches 0. Let's write similar statements saying that the limit of this graph as x gets really big is 1.5. First, let's write the correct limit equation for this function. We're saying that the limit as x goes to infinity of g of x equals 1.5. Let's draw a narrow tube centered at 1.5 and suppose it has width epsilon. This statement said that our earlier function, 1 over x, stayed inside a tube centered at 0. Let's replace the function 1 over x with g of x. But what numbers should we write over here and over here to say that g of x stays inside this tube that we've drawn? Exactly. Here's how you say this function g of x is inside the tube centered at 1.5. 1.5 minus epsilon is less than g of x is less than 1.5 plus epsilon. Now the 1 over epsilon you found earlier was for the function 1 over x. So next, we'll look at how to change this part of the limit statement so that it's about this function here. So we've been saying that 1.5 is the limit if, for any tube width epsilon, the function enters the tube and never leaves. Let's suppose epsilon is equal to 0.8. Find a value of n so that beyond n, the function is always inside the tube. Remember that when the function is always inside the tube on this screen, the tube will turn blue. Great! Now let's suppose epsilon is smaller, let's say 0.4. Once again, try finding a value of n so that beyond n, the function is always inside the tube. So when the tube is centered at 1.5, for any value of epsilon, which is the width of the tube, you're able to find a value for n so that f of x is inside the tube for all x greater than n. For the tube that's drawn here, here's a value of n that works. For all x greater than n, f of x is inside the tube. So these inequalities are true. If we change all the 1.5s here to the letter L, then we have expressions that work for any number. So this is what it means to say that the limit of a function as x goes to infinity equals a number L. It means that for any epsilon greater than 0, there's a number n such that for all x greater than n, f of x is between L minus epsilon and L plus epsilon. Let's return to the function 1 over x. To find the limit as x gets really big and goes to infinity, we used an infinitely long tube in the positive x direction. We can also look at the limit as x gets more and more negative, and we can write that like this: the limit as x approaches negative infinity. Which of these tubes here do you think could represent the limit as x approaches negative infinity? Right, so everything we've said about limits to positive infinity also works for limits as x approaches negative infinity, but remember that the tube goes in the negative direction. Let's look at another function, and let's call it f of x. Suppose the limit as x goes to positive infinity of f of x is equal to a, and let's say the limit as x goes to negative infinity of f of x is equal to b. These two horizontal lines, y equals a down here and y equals b up here, are called horizontal asymptotes. Asymptotes are lines that curves get really close to. And because these asymptotes are horizontal, they're called horizontal asymptotes. Once again, here's the function 1 over x. This function has exactly one horizontal asymptote, and its y equals what number? You've done some excellent work here, and you've seen how to take limits as x goes to infinity and as x goes to negative infinity. Let's look at one last function, the sine of x. The sine function oscillates across the x-axis, meaning it keeps going up and down. How would you describe the limit as x goes to infinity of this function? To see if you've found the limit, set the center of the tube and see if the function enters and stays inside the tube as you make the tube narrower and narrower. Nicely done. So as you can see, not every function has a limit as x goes to infinity. There's no single value that the sine function approaches as x gets really big, and so the limit as x goes to infinity of the sine of x does not exist.